Good morning, everyone. Today I'm excited to talk to you about our decisions to build a wind power plant in Grotta, Iceland. Iceland is a country with abundance of natural resources, including geothermal energy, hydropower, and wind power. And in recent years, Iceland has made a strong commitment to developing its renewable energy resources, and we believe that wind power is a key part of this strategy. Grotta is an ideal location for wind power plant for several reasons. Firstly, the area is consistently windy, as you can see here on the map, with an average wind speed of over 8 meters per second, and also above 9 here. This means that wind turbines will be able to generate a significant amount of electricity. Second, the area is relatively remote. As you can see, here is a small, I guess you could say, island outside of the community, which means there is minimal impact on local communities. Finally, the Icelandic government has a supportive policy framework for renewable energy development. I found this document here on the web, Iceland's Sovereign Sustainable Financing Framework, and put it into BARD. Here is a shortened version of it, basically saying the government has set a target of generating 100% of its electricity from renewable sources by 2035. And the report will include information on the projects that have been financed, the environmental and social benefits of the project. One of the major advantages of building a wind power plant in Grotta is that we will not have to build any infrastructure to connect it to the coastline. This is because Grotta is already located near a major transmission line that will save a significant amount of time and money. As you can see here on the map, it is indeed located next to this small community with a road going all the way to the lighthouse, and there could wind power plant be built. As I mentioned earlier, Grotta is a very windy area. In fact, it's one of the windiest places in Iceland. This is because of the unique topography of the area. The mountains and valleys in the area create a funnel effect that concentrates the wind. This makes Grotta an ideal location for generating wind power. As you can see here on my topography map here, let's see. There are a lot of mountains and using them, and they are to our advantage. As you can see, the wind flowing through the mountains there as like a funnel, and over Reykjavik, where our wind power plant would be. In conclusion, we believe that wind power plant in Grotta is a wise decision. It is a project that will benefit the Icelandic people and the environment for generations to come, as wind power can create jobs in the local community.
Okay, and then we're going to focus in the energy section, which here is important to know that the cost of the wind energy is measured in euros per kilowatt hour, especially because our location is Iceland and it is located in Europe. And then we're going to assume that our electricity of this wind farm is going to be sold at an annual rate of 0.07 euros per kilowatt hour. Okay, then here in the left side we can see that the Retscreen program had made 5 different projects, each one with a different wind speed, but we are going to focus on the second one because, as we can see in the location where we've got the climate data, it says that our average wind speed is 6 meters per second. So the other ones we're going to deleted them so as not to have confusions in our final calculations. Okay, now in this energy section we've got 3 levels, and we're going to make a first modeling of 100 megawatts so as to later, when we've got when we have finished this model, reduce to 50 megawatts, which is the one that interested us. But we decided to skip the level 1 because there's not so much information to know, and we focused the most of our project in level 2, which this calculates the electricity production and the capacity factor based on inputs describing the annual wind resource and the performance of the wind turbine and other equipments. So here it's important to add the wind speed. It's true that the Retscreen speed average was 6 meters per second, but we focus on the ones that appears in the global atlas, measured at 10 meters, and based on a wind shear exponent of 0.14. But as we can see here, the hub height of our turbines measures also the wind speed at 100 meters, that it is the one that really interests us, and it is 10 meters per second. Here we have to decide of a manufacturer and a model of wind turbines, and the one that we chose is the manufacturer XEMC with a hub height of 100 meters, perfect, rotor diameter per turbine of 115 meters, and it's true that the power doesn't appear, that this data doesn't appear here, but there's nothing that the internet can solve. So we found it in the internet, this data, so as to make this power curve. And this power curve relates the instantaneous power output, which is this in the table, to the instantaneous wind speed. And it is focused in this table and shown in this graphic, in this green line, more specifically here, which, well, as we can see, there's no power generated when the wind speed is lower than 4 meters per second, and it also maintains a rated power of 5 megawatts once we arrive at approximately 14 meters per second. Well, that's interesting. And finally, here in this level 2, we can see our losses and that we have a capacity factor of 43.6%. The capacity factor means how much electricity a wind turbine or a wind farm can generate over a period of time. So in our case, we can generate like around 43% of its maximum theoretical energy output over this period of time, which is quite good a quite good capacity factor for a wind turbine. And these factors that can affect this capacity factor, having this or another one, it could be like speed, well, the wind speed, the size and efficiency of the turbines, the number of turbines. And in our case, we wanted to have the power capacity of 100 megawatts in this first modeling. So if the power capacity per turbine of this model is 5 megawatts, the number of turbines needed would be 20 in this first case, and our electricity production per turbine would be this number of, well, around 21,000 megawatts per hour.
Okay, now we're about to calculate the cost and make evaluations of the projects. The cost calculation has 3 levels. We decide to start from the level 3 because the level 2 and level 3 take the initial cost apart into components. It would be more accurate to calculate the cost. And the level 1 will help, the level 3 will help me gain the maximum details. For initiate cost, we would enter 3 million euros, and we will assume 5 million euros for development and 2 million euros for engineers. This software provides us with the project capacities we set and the energy page. I will enter the cost per kilowatt in this blank. And back to the energy part. By clicking on the dollar sign, the software shows the cost per kilowatt for 100 million watt is 2,000 euros. To make much budget, we set the cost of 2,300 euros per kilowatt. Then we measure the distance between Grodad and the city center through Google Maps. Here is the result. So I entered 5 kilometers in the transmission line and 20,000 euros per kilometer. And we decided one substation which costing 2 million euros. Then on the balance of system in miscellaneous, with less specific project cost for wind turbine installation. It's open two lines, foundations and turbine erections. Both the number of them are set as 10. We assumed 4.5 million euros per turbine foundation and 2 million euros per turbine. And we assume there will be one transportation project that costs 3 million euros. Concluding the video provided by the software engineer, 5% contingencies is a typical figure for a wind farm, so we use 5% as contingencies. Because of the project is a long-term project, we set a relatively high interest of 8% over 12 months construction period. Now it's nearly 33,000 euros for the initial cost. The O&M cost, which means operation and maintenance cost. In this part, we use the figures. This software provide to us is 3.6 million euros. About the periodic cost, we assume 20 years into the project, costing 3.5 million euros.
Well, it's also important to take into account the emissions in our area. Specifically in Iceland, we've got a greenhouse gas emission factor of 0.17 tons of CO2 per megawatt hour, which is significantly lower than the average of 0.46, and this is because the use of renewable sources in this country. And then the greenhouse reduction credit rate in this location is 11.9 euros per ton of CO2.
Then we open the finance page. We can see the pre-tax IRR equity is 0.66%. This figure even lower than some stocks. So if the pre-tax is like this, maybe no one will spend money for these projects. And the net present value should be 0 to make profit. So we need to do some adjustments.
Okay, so for the next step, we're trying to get the net present value down to 0, as we have managed to do here. The value was not profitable, it was a lot below 0 before doing some changes. So to find out how much money per kilowatt we would need to get to make this thing profitable, we did this necessary cost reduction for profitability here. And in this case, we needed to add 1,395 euros and a set amount of cents to make this profitable. This number will probably be a lot different with the 50 megawatt configuration instead of the 100 watt configuration. Okay, so now we will be changing our power capacity down to 50 megawatts instead of 100. This will be done by going to the energy section and reducing the turbines from 20 down to 10. as you can see, that drops the power capacity down to 50. Since we have 10 less turbines, we will have to do some changes in the costs as well. So let's start with this. The foundations and wind turbine erections will need to be lowered to 10 as well, as you see here. And then we need to check the necessary cost reduction for profitability, since we're only having 50 megawatts instead of 100. So let's change it to 50. And now we see that with the same amount of money per kilowatt added, we still have a net present value that's below zero. So we will need to be adding some more cost reductions to make this profitable. So that's what I'm going to be doing next. And now, after some digging around, we found the necessary cost reduction for profitability to be 1,555 euros and a couple of cents, which brings the net present value to zero. And as stated earlier, that's calculating how much money per kilowatts that's needed for the power plant to actually be profitable.
In summarizing our initial and improved versions, we implemented several changes. Primarily, we reduced the number of installed wind turbines from 20 to 10, resulting in a 50% decrease in power capacity, from 100 megawatts to 50 megawatts. Our goal is to reach net present value zero, meaning the amount of money needed per kilowatt for our power plant to be profitable. Despite this adjustment, our annual savings remained in the negative range. Consequently, we implemented additional cost reductions to ensure profitability. Necessary cost reductions was changed from 100,000 to 50,000, meaning it would go from 1,395 euros to roughly 1,555 euros. This was the final step to achieve net present value zero. In conclusion, our team completed a thorough pre-feasibility study for a 50 megawatt wind power plant using Retscreen Expert. We started with a 100 megawatt model, refining it as we did the project. The software guided us through energy modeling, cost analysis, and wind resource assessment, considering factors like wind speed and location roughness. Real-world market dynamics were crucial, and we Googled electricity purchase prices, acknowledging their volatility. Sources like Nord Pool and electricity prices provided valuable insights. We also had to look up the price for wind turbine parts and installation costs.